All right, today what we're going to do is we're going to learn about recurrence relations. Now, this video I think might be a little bit longer. We're going to go at a slower pace because I'll be honest, recurrence relations, they can be a difficult concept to grasp, right? But that's not to worry about because what we're going to do today is we're going to go, like I said, at a slower pace. We're going to hopefully make sense of this abstract concept. And if you came here specifically for help with recurrence relations, I hope that by the end of the video, we will know everything there is to know about at least first order recurrence relations. Now, let's finally define what a recurrence relation is. Now, a recurrence relation, it is a formula, right? What kind of formula is it? It's a formula that specifies how each term of a sequence of a sequence is produced from earlier terms. Now, what exactly do I mean by that? Well, let's look at an example, right? Say I have a sequence, right, where each term, call it a sub n, is equal to 2a sub n minus 1 plus 2 times a sub n minus 2. Now, you can't figure out what a sub n is unless you're given some initial conditions, unless I tell you what two terms already are, right? So let's write out what those terms are, right? So I'll say, let's say a sub 0, which usually if you have a subscript that is 0, people will say not, and that's what I'm going to say. So I won't say a0, I'll say a naught. So a naught will be equal to 4, and a1 will be equal to 3. Now what we're going to do is plug that into our formula for an, right? So we have an is equal to 2 times a, or so here, let's say an, we're going to solve for a2, right? So a2 is equal to 2 times an minus 1. Well, an minus 1 in this case is just a1. So this is 2 times 3, right? And then this is going to be plus 2 times a sub n minus 2. N minus 2 is equal to 0, so we want 2 times a naught. So this is going to be equal to 4, right? And so then a2 is going to be equal to 2 times 3, which is 6, plus 2 times 4, which is 8. So 6 plus 8, what is that? That's 14, right? There you go. And now what we could do is we could solve for a3. So a3 is going to be equal to 2 times a sub 2, right? Well, we just solved for a sub 2, right? It's 14. And then that's going to be plus 2 times a sub 1, right? What was a sub 1? That's what we were given. We were given that that's 3, right? So this is 2 times 14, which is 28, plus 2 times 3, 6. 28 plus 6 is equal to 34. Oh, I meant to change that back to yellow. I didn't. Oh well. And as you can see, we could keep on doing this, right? We could solve for a4, a5, a6, right? But we don't want to have to do all of that, right? We want to have an. It's a lot of work, right? To just keep on solving for terms based on previous terms. We want an written in terms of n, right? So we want it written in terms of something that just is based on n. So we don't have to rely on previous terms, right? We could just say, oh, n is equal to 5. Well, then an is equal to blah, 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 right? Now, how are we going to actually get an explicit formula for n in terms of n? Well, what we are going to do is we are going to derive that formula ourselves, right? And then I'm going to show you the general formula because we do have one, right? So let's look at an example, right? And remember, so because we're doing first order recurrence relations, our a sub n, here let's say a sub n, is going to be based only on one previous term. And the simplest way to do that is just say an is equal to s times a sub n minus 1, where s is some coefficient, some constant coefficient. So this is a first order recurrence relation. Up here, when an was in terms of an minus 1 and an minus 2, this was a second order recurrence relation, right? That name makes sense because an was defined by 2 previous terms, right? We're going to talk about 1 previous term. So if we have an, right, and this is equal to s times a sub n minus 1, well, that means that each term of the sequence is just equal to s times the previous term, right? So let's look at something, right? Let's say we have a sub 3, right? That's going to be equal to s times a sub 2, right? A sub 2, right? This is just equal to s times a sub 1. But a sub 1 is just s times a naught. And we can't go any lower than that. A naught is like our base case, right? As you can see, right? N is equal to 3, right? And I have 1, 2, 3 s's multiplied by s n times, and ultimately end up back at a naught, right? So if I want to write a general equation real quick, what I could say is, here, let's write this in a different color. I could say that an will be equal to s to the n times a naught, right? So that's just, and then what basically, if this was like a real problem, I would have been given a value for a naught, right? Say a naught is equal to 3, right? Then basically I would substitute that for a naught. So let's just pretend I said a naught is equal to 3. Then I would substitute that and say s to the n times 3. S to the n times 3, right? And now I got exactly what I wanted, right? I got an explicit formula for the term a sub n in terms of n, right? Now remember, s would be a constant we're given. I just wrote s because it's general, right? S could be 7 or 1 or 5, right? But the fact of the matter here is that I got my explicit formula for an. No longer is an written in terms of an minus 1, it's written solely in terms of n. So if I were given a value of n, I could immediately solve for the term in the sequence an. Now, that was pretty easy, I think. We're going to do a little bit more of a complicated example, right? Because things in life, they're not always easy. We need to know how to face these more difficult problems. So here's the example I'm going to give you. I'm going to say a sub n is equal to 2 times a sub n minus 1 plus 3. Isn't that a little silly? Isn't it a little silly how all I did was add another constant to the end of this, and that means things are going to get difficult. So, how do we derive our equation for an? Well, as we saw in the previous example, we found a pattern all the way down to our base case of a naught, right? So we want things in terms of a naught because a naught will be given to us and will thus be a number. And in the end, we could just plug that number in and everything will be in terms of n. So since we want everything in terms of a naught, let's first write out a few terms, right? Let's write out what a1 is, right? Well, that's going to be 2 times a naught plus 3. All right, not bad. What's a2? A2 is 2 times a1 plus 3. Remember, a1 is 2 times a naught plus 3, right? It's this right here. So plugging that in, we get 4 times a naught plus 6 plus 3 is 9. Now let's do a3. This is going to be 2 times a2 plus 3. Substituting in what we solved for a2 in terms of a naught, we get 2 times, we get 2 times this whole thing, right? So that's going to be 8 a naught plus 18, and then plus 3, so we get plus 21. All right, let's do a4, and I think this will be the last one. This is equal to 2a3 plus 3. Plugging in what we have solved for a3 in terms of a naught, it's going to be 2 times 8 a naught, that's equal to 16 a naught. 2 times 21 is 42, plus 3 is 45. All right. What do we have here, right? What do we have here? Well, let's look at something. How can we generalize this in terms of n? Now, what I like about this example is we have a more obvious part and a less obvious part to our answer, right? Because if we look at our n's, right? If we look at our n and then the coefficient attached to a naught, right? 1, 2, 2, 4, 3, 8, 4, 16. Clearly, maybe not clearly, the coefficient in front of a naught is doubling every single time, right? 2, 4, 8, 16. I bet you if you solved for a5, you would have 32 a naught, right? So it looks like the coefficient in front of a naught, right, is doubling each time, right? It looks like our coefficient is 2 to the n, right? I mean, like, just look at our thing. Like, if we plug in, if n is equal to 2, right? So if n was equal to 2, then we get 4a naught, right? Which is exactly what we have right here. If n was equal to 3, we get 8a naught, which is exactly what we have right here. So I'm claiming right now that this is 2 to the n, and hopefully you would believe me on that. But there's something way less obvious, right? What? How are 45, 21, 9, and 3 all related, right? How are they related? Well, the next natural question to ask is, well, where did they come from, right? Where did 45 come from? Well, let's figure that out, right? It seems like a good thing we should try and figure out. 45, right? So we have A4 was equal to 2 times A3 plus 3, right? But then we substituted in for A3, right? So this became 2 times 8 A naught plus 21 plus 3. So 45 came from 2 times 21 plus 3, right? Let's write that out. So now we have 45 was equal to 2 times 21 plus 3, right? But then where did 21 come from, right? That's one of the numbers we're trying to solve for. Well, it came from the previous term, the 9, right? 21 is equal to 2 times 9 plus 3. Where did the 9 come from? The 9 came from our previous term, 3, right? So 9 is, we have 2 times 2. 9 is 2 times 3 plus 3. And then we got to make sure we have all of our previous plus 3s. And there we go. And this is still, this whole thing I just wrote out is still equal to 45, right? So there we go. It looks like everything is coming from 2 times 3 plus 3. Now, we can simplify this expression a little bit, right? Now, I'm going to write out what this expression simplifies to. If you need to convince yourself of the answer, that's perfectly fine. I had to do the same thing, right? So I would recommend, after I write this, pausing this out and simplifying this expression to see if we get the same thing. So it turns out that this will become, hopefully I don't mess this up, 2 cubed times 3 plus 2 squared times 3 plus 2 to the first times 3 plus 2 to the 0 times 3. Really hope I didn't mess that up. I think I'm going to try to convince myself, right? So basically in our innermost parentheses, we have 2 times 3 plus 3, right? But then we have a 2 out here that we need to distribute to our parentheses, right? So this now becomes, I believe, this would become 2 squared times 3, and then this would be 2 times 3, and then we have a plus 3. Yeah. And then when we distribute our outermost thing, we get 2 cubed times 3 plus 2 squared times 3 plus 2 to the first times 3 plus 3, which is the same thing as 2 to the 0 times 3. Okay, I convinced myself. If you need to convince yourself, that's perfectly fine. Spend some more time on it, right? But now, what we could do is we can pull a 3 out of this whole thing, right? So this can become 2 cubed plus 2 squared plus 2 to the first plus 2 to the 0 times 3, right? And this can be simplified. I'm pretty sure we proved this. Here, let's say this is going to be equal to 2 to the 4th minus 1 times 3. And I'm pretty sure we proved that those two things are equal in our induction video. I'm pretty sure, or maybe we did it in the combinatorial proof. I think we did it in the combinatorial proof video because that would actually be not too difficult of a combinatorial proof to do. Basically, 2 to the 4th minus 1 can be, or 2 to the n in general terms minus 1 can be all subsets of an n-sized set, disregarding the empty set. And then you could show that this sum up here will also count all subsets disregarding the empty set, or disregarding one of the sets. And I think in this case it would be the set of size n. So that would be a quick combinatorial proof for you to do. Anyway, we're getting distracted here, right? So we got our formula for 45, right? It was 2 to the 4th minus 1 times 3, right? And so remember, 45 was in our A4 term, right? So right now what we're looking at is A4 is equal to 2 to the 4th, A naught, right? And then plus 45. 45 is equal to 2 to the 4th minus 1 times 3. So it looks like here, there's a lot of 4s here, right? It looks like this is supposed to be a 4. It looks like a to the n will be 2 to the n, a naught, plus 2 to the n minus 1 times 3. To make this a little simpler, right? Let's multiply our 3 out, right? So we have a to the n is going to be equal to 2 to the n, a naught, plus 3 times 2 to the n minus 3. There we go. And now what we can do is undistribute our 2 to the n. So basically this is 2 to the n times a naught plus 3 minus 3. And there we go. We're in simplest form. And now, like I said, maybe I would give you something, well, definitely, I would give you something in the beginning like a naught is equal to 1, for example, right? Then our final equation would say 2 to the n, 1 plus 3 is 4, minus 3. And now we have exactly what we wanted. We have our term a sub n written in terms only of n. But you still might be asking yourself, okay, Johnny, that was some complicated work. I'm still trying to wrap my mind around that, right? And maybe I even do have my mind already wrapped around that idea. But how can I be sure that 2 to the n times 4 minus 3 is always going to give me the proper term, right? I can always double check. I can double check that with our original formula, right? That was written explicitly in terms of a previous term, right? So how am I going to show that in general this holds, right? Well, you could do a proof by induction, but guess what? That would suck, right? Nobody wants to do a proof by induction after doing all that work just to find our relation. We don't want to then do a proof by induction every single time, right? It doesn't matter. And like I said, there already is an explicit formula for first order recurrence relations. And I'm not going to ask you to reinvent the wheel every single time you do a recurrence relation, right? That doesn't make sense. So here's what I'm going to propose, right? So here, let me write this in a different color, right? Let's do a nice light pink. Proposition. What I'm going to say is if we have a term a sub n, right? And it is a first order recurrence relation of the form s times a sub n minus 1 plus some constant t. So s and t are constants, right? Then our a sub n, right? Here, let's write this next to it. Then a sub n will be equal to c1 times s to the n plus c2. There are way more letters here than numbers, and we're supposed to be doing math, so what's going on? All right. Basically, C1, S, N, and C2, they're all numbers, right? They are all going to be constant numbers. This is just our general formula. What do we do when we've just got a general formula that doesn't make sense? We look at an example, right? So our example, right, is going to be 5 times hold on. First, we should write a sub n is equal to 5 times a sub n minus 1 plus 3. Okay, so in this case, right, we're of the form s a sub n minus 1 plus t. So in this case, s is equal to 5, right? So looking at what I proposed, looking at what I found right here, then a sub n should be equal to c1 times s to the n. Well, s is 5, so 5 to the n plus c2, right? So there we go. That's what we're proposing, right? But how do we actually check that, right? Well, again, you need to have some kind of initial condition, right? So what I'm going to do is tell you that a naught is equal to 1, right? That's what my initial condition is going to be. Well, if a naught is equal to 1, here, let's write this, let's stay consistent, let's write this in yellow. If a naught is equal to 1, then this is going to be equal to c1 times s to the 0 power, because that's what n is, plus, I guess this should technically be a 5, because we know what s is, plus c2. 5 to the 0 is 1, so this is just equal to c1 plus c2. Great. Now a1, right? What will a1 actually be equal to? I just had some crazy recording issue happen. I don't know what happened, but anyway, so a1, right? Looking at our recurrence relation, a1 is equal to 5 times a naught here. Let's get our yellow back. A1 is equal to 5 times a naught plus 3. So a naught was 1, so 5 times 1 plus 3 is 8. But again, this should be written in terms of c1 and c2. So this is going to be equal to c1 times 5 here. I got to make sure, I got to make our 5s and s's distinguishable. So c1 times 5 to the first plus c2, right? So this is just equal to, I'm just going to write 5 on the left side now. I don't know. 5c1 plus c2, right? We want to solve for c1 and c2 so we can have our general equation. How are we going to do this? Algebra 2, baby. We have a system of equations right now, right? So this is some algebra 2 stuff. So hopefully you know how to solve systems of equations. If not, that's all right. There are other videos out there online explaining them. Not me, but I'm sure you could find them. So we have 8 is equal to 5 times c1 plus c2. We also have 1 is equal to c1 plus c2. We want to solve for our variable. So again, I'm going to do this fast because technically speaking, you should know how to do this if you're doing discrete math. But again, it's all right if you don't. That's fine. But technically you should, so I'm going to move through this pretty fast. So subtracting our second equation, our bottom equation from our top one, right? We get 7 is equal to 4c1, right? And then solving for c1, we get 7/4 is equal to c1. Now what we're going to do is we're going to plug this into our formula for 1. So we're going to say 1 is equal to 7/4 plus c2. Oh, why am I writing like that? Plus c2. And if we subtract 7/4 from 1, we get -3/4 is equal to c2. So now that we've solved for c1 and c2, we could say that an is going to be equal to 5 to the n times c1. So that is what? 7. What did I say c1 is? It's 7/4, 7/4. And then c2 is -3/4. So we say -3/4, and boom. We just solved for an, and it was way simpler, way faster than what we did before because we have this general formula. So you're welcome. But now, what about when s is just 1, right? We haven't covered that case. Well, when s is 1, I'm going to make a little proposition, and that's where I'm going to leave you for this video. It's actually really nice. Proposition. There we go. When s is equal to 1, right? So when an is simply equal to a sub n minus 1 plus some constant t, this will imply that an is equal to a naught plus nt. And that's obviously that's way easier. We don't have to solve for c1 and c2. We're given our t, a naught, and n. So boom, you would already be able to know what the nth term always is. And that is where I'm going to leave you for this video. So there we go. That was everything there is to know about first order recurrence relations. As you can see, it's like a bit of time. In the next video, what we're going to do is we're going to talk about second order recurrence relations. So if you made it to the end of this video, thank you for watching. I really appreciate it, and I hope you learned something.